No, it's my 3s and my 5s that I...
Did you get 0.485?
But you're right here, this is like kind of like a sort of scenario. Like if you want your answer to be within 5 inches.
All right, guys.
The point that will
Yeah.
Let's take a look at number 1.
So you need
0.4847.
So number 1,
Yeah, I asked you.
what's X bar?
6, right?
Cool. Here we know the population standard deviation 2.5. N is 37. Why is it okay to use Z-scores here? Why? There you go.
Yeah.
Plus, even if it didn't say it was normal, why is it still okay?
And it's ultra 30.
Good, central limit here. We got greater than 30 sample size. I
0.045,
like it, but it says it's normal, so it doesn't even matter.
So what's the Z-score for
I like it. Now the Z-score, we did this one earlier, 95% Z-score. What did we figure out? What did you guys get?
1.96.
1.86. So, now why is a negative not matter? There's a positive one and a negative one, and they're both in the formula already. So all I really care about is the value of Z, that number. So then I just have to plug and shove. You guys all right? So normally the only thing I don't know, the only thing I'm not given is Z.
Q hat.
So now I got 68.4, give or take.
Q hat's what?
1 minus
Why?
Q hat.
Why?
That's reasons. Because that's not Q, it's
Now,
Q hat.
technically you
So
don't
it's 0.515.
have to do the error first, but like I said, the book will sometimes ask for the error by itself. I'll sometimes ask for the error by itself. You might as well just calculate the damn thing. And it makes it easier. We'll see in a minute. I can make a comparison with what we're going to do down here. What did you guys get for this error? It was like 8056?
Yep.
806? It doesn't matter. So then you get what little interval? 60 what? 67 points. Let's try this again. It's 67.594 makes sense. Up to 9.206, right?
185.
Remember, I'm up to 4 places.
No, I did, instead of 515, I did 151.
Now guys, real quick question. If I wrote those the other way around, is that all right?
No.
No, of course not. Intervals small to big. Secondly, how many intervals have I written up there? 1. An interval is a bottom and a top, a ceiling and a floor. It's min to max. That is 1 interval, right? So when you write your conclusion, we don't say we're so confident that it's the intervals. There's no intervals. There's one interval. So how do I write this conclusion? We are 95% confident. Good, that the intervals 67.594 what? Inches to 69.206 inches. Contains the true mean height
How'd you get 0.0335?
of good.
Error.
Huh?
True mean height.
That's P hat plus.
P hat is that. How's that?
P hat is this.
Yeah.
So point,
Okay.
yeah, and that equals, yeah, divided by that. Yeah, and I got 0.0.
Now-
Let me check.
On the second one, does it make? I really want to make sense. If I put 0.806 in here, I will get n equal about 37. I already know that. I already know that a sample size of 37 leads to this error. I don't want this error again. I want to be within half an inch. So should my answer be bigger or smaller? You guys already did it, so you know it's going to be bigger. Well, why is it bigger? Because I want to be even more sure. I want to be less error. So to do that, I got to have a larger sample to do that. That should make sense. You guys knew that coming in on day one. Bigger sample, better. So now just plug everything in. Z is the same thing. I'm still at 95% confidence, so 1.96 squared with sigma 2.5, and now I want the error to be 0.5. I like it. So what did you guys get? You got like 96 point something, right?
Yeah.
96 point blah, blah, blah. Always round that sucker up. So what if I would have said how many more men do you need?
Track 97.
Yeah, 97 minus 37. You need 60 more dudes. I like it.
You always round up.
Yeah, and the reason we always round up is in order to be within half an inch, I have to have 96.0 something, right? I have to have that many. So if I just do 96, now I'm not within half an inch. I'm a little more. So you always round up so you go even better. You always round up to go even better. Yes?
So this one we rounded up a whole number because it's men. The previous example we did was we rounded up to 1 cent, right? So 0.01.
Yeah, n is always a number of things. N is discrete. 0, 1, 2, 3. So here it was talking about gas prices, but what did n represent? Gas stations. So that's a number of gas stations. I'd have to go look at 209 gas stations total to be within 5 cents. Is that cool? That's a number of gas stations.
Oh, that's not 2.0?
No,
Oh,
the little 2 dude has got, yeah. All right. Good, use that. All right. Let me stay up here to talk about this next stuff. So there's 2 things to talk about down here. Guys, there's 2 things to talk about down here. One of them is this, which is actually the most important thing. Because what's the thing that tells me I can do anything up here? What do I have to check to make sure I can do anything with this kind of problem? I have to know that it is normally distributed, or at least normally enough, right? So we have a way to check. We have the central limit theorem. If it doesn't say it's normal, we can look at the sample size to see if the sample means are normal enough. We have to have that kind of a check for percentage problems also. So there was that handout with the flipping a coin. This guy. Now, this is interesting. You okay?
Yeah.
I'm sorry. This, remember this picture? This was flipping a coin 14 times. Would you say that that looks pretty normal? Hell yeah. In fact, according to the requirements we're about to talk about, this is normal enough. I could actually use z-scores and look at the z-score chart to get areas for this. So, what is this requirement? So why is this normal? It's got room to go up and then come back down. What was the mean on this piece of paper? You guys remember? Let me put it up here. The mean on this, of course, it was 14 times flipping a coin, so the mean is 7 heads. Makes sense? You with me? What if the and what course? What's the tallest bar? 7. To be honest, the tallest bar will always be the. Sometimes it won't be the mean, but it should be very close to the mean. But if the mean for this, if I had a different situation where the mean was 1, is that enough room for it to go up and come back down? So if the mean was 1,
Someone dying?
Yeah, what the heck?
slowly. If the mean was 1, then the highest bar should be right around 1 somewhere. Is that normal? Does that look normal? That is skewed, right?
Move it.
Not normal. So, watch this idea. If I get the mean to be at least, or more than 5, I can't remember this book, which way it says it, to be honest. Oh, screw it. I'm going to say it the way I was taught. If I get the mean, and remember, what was the mean formula for NPQ? What was the mean?
NP.
NP. So if NP is at least 5, And see, I really want this to make sense. If it's at least 5, if the mean was at least 5, that means the highest bar would be a 5. That gives it room in front of it and room after it to go up and come back down. And then it would be normally enough. So it's really just pulling it away from that 0 wall. Why is that 0 wall there? Because this is a binomial thing. What's the least you could have? 0. Right? So I got to pull it far enough away from the wall so it can go up and come back down. Now, there is another wall. What's the other wall? Where would the other wall be for this problem here? The least number of heads I could have is 0. The most, there's another freaking wall right there. Shit. So I got to make sure that it gets away from this wall enough, but I also I can't let it get too close to that one. And to be honest, that's looking at NQ, the number of failures. I don't want the number of failures to be too small, or else that makes it push up against that other wall. So when I say check NP and NQ, this is the check to make sure the binomial situation is normal enough, is NP and NQ have to be at least 5. So it's just like checking to make sure n is greater than 30 before you do shit, right? Here you got to make sure that NP and NQ are bigger than or equal to 5 before you do stuff. That's what tells me it's normally enough, and that's what tells me I can do the z-score stuff for the formula. All right, so that's one thing we had to talk about. So even if none of that made sense, which would make me cry a little bit, it's all right. I'll get over it. Probably then greater than 30 didn't make sense, but at least now you know just to do that, just to check that. So what do you check for this? You check that. Same idea as checking to make sure n is greater than 30. Same idea.
Oh shit.
All right, so what happens on this problem here? What's n?
652.
No, what's n? Yeah, 652. What's n always?
652.
The total number of things in my sample is 650. 316 of them did something interesting, but I had to get all of these people to find these people. Right? So n is 652. What's p? Do we know yet?
0.91.
Now watch this. So how do you get p and all right. Now here's another little thing, right? What was the difference between mu and x bar?
Sample population.
Mu is the population. X bar is the sample. P is population. We've used P this whole time. P with a little hat on it. That's the actual name. P hat. Right? The hat you don't want to wear. P hat is the sample percentage. The same way that X bar is a sample mean. It's the same kind of idea. No matter what P and Q are wearing, what articles of clothing they have on, they must add to be 1 because they're success and failure, right? You good? So just looking at what I tell you, could you figure out the percentage from the sample? How do you figure out the percentage? Yeah. So the number of successes, the X, 316, divided by 652. And what do you get for P hat then?
0.4846.
485.
485?
Yeah.
Yeah.
And Michelle, it's awesome. It's almost like I planted you, which it didn't. You always take P hat in this kind of problem. You take it out at least 3 places.
Gucci.
So if you go 4, you're still fine.
No, you're not.
Remember what I said earlier this semester? Just take everything out to 4 places. You're golden if you just want to do that. So what's Q hat? Do I have to do any real work to figure out Q hat?
1 minus P hat.
1 minus that. Yeah.
Can you do
0.515.
this one so I can try that?
And of course, n is 652. Now watch. Let me see if some of you guys get this. So I have to check n times p hat.
Yep.
But what the hell is n times p hat going to be? If you don't believe me, you can actually calculate it and get some of it, but it's going to be 316. So what do you think n times q hat's going to be?
652 minus 3.
Yeah, the other ones. NP hat is the successes, and NQ hat is the failures. So sure enough, NP hat is 316, which is at least 5. NQ hat is going to be, what, Jeff? 336, which is at least 5. Check. So what does this mean right here? What does all this mean? What does that mean?
more than 5.
That's awesome. That means there are at least 5,
It means they're normal.
which means it's normal enough.
Wait, didn't it have to be 30?
I'm allowed to translate the confidence level into a z-score. I'm allowed to use a z-score chart to do that. Yes, ma'am.
So to factor NP and subtract.
Yeah. I really want that. NP is going to be the successes, so NQ must be the other people or the other thing.
So you're not.
You could actually multiply it and see if I'm full of shit or what. It's always an option. If you do 0.485 times 652, I hope to God some of you guys realize, of course it's got to come out to be close to 316. It's going to be perfect because we rounded this, right?
1,805.
Cool. I like it.
Mama did it
So you can always just fall back on the formula if you're not remembering, but otherwise you just got to pull the number out of there and get the other part. They got to be at least 5.
Oh, shit.
So how confident do I want to be in this problem? I want to be 91%. So take a minute and figure out what that z-score is. Some of you guys already did, so just be quiet. We've done that in class once and on the test once.
Right there, one.
What's up?
How'd you write it? 91% confident that the interval contains true mean.
That the interval blah percent?
Yeah.
So blah percent. Percent
Percent.
are your units.
So you have to move it over.
Percent, yes. Change the decimals to percentage. All right. So what'd you guys get for the z-scores? 1.7. So now, here's the other part. Here's the part I haven't talked about yet. Where the hell did that formula come from? Look at that weird shit. All right, so let's talk about it. So this is the formula we're going to use. You know me. I'm not just going to give you a formula, even if you want me to. Just give it to you. Because it's easy enough to just plug shit into there. That's great. I have to show you where the hell it came from. So remember where we started today. We started today here. I don't know if you guys remember. And then we started doing stuff to this. Okay. Now, if I'm talking about means, we would take a sample, we have to change the standard deviation, all kinds of stuff. But now I'm talking about NPQ kind of problem. So what is X bar? What's mu for an NPQ problem? We said this earlier. What's mu? NP. So then what's X bar? It's going to be NP hat. That's going to be my sample mean is N times my sample percentage. So that's going to be NP hat. Oh, and let me do something else that's a little bit... What's the purpose of this again to do? To try to figure out where mu is, right? So see, I'm going to do mu is somewhere in there. Is that okay? It's going to become incredibly important in a minute. And what's the mu? Of course, the mu for NPQ problem is just NP. Is that cool? Plus or minus Z. What's the standard deviation for an NPQ problem? Basically just gave it away. Yeah. Square root of N, and now it's going to be P hat, Q hat.
NP.
Let me stop.
So, mu. That's right.
So we developed these confidence intervals starting from the same idea. Really the definition of z-score. But I put in what they all look like for an NPQ problem. Now, I don't want a confidence interval for NP. I want a confidence interval for the percentage.
Yeah.
So of course, what do I need to get rid of? I don't want a confidence interval that catches NP. I want one that just talks about P. So I got to divide by N. Just to remind you guys, I do this a lot, and I know you love it. You're deriving a formula. You are not going to have to do what I'm doing right now. I'm showing you where a formula is coming from. That cancels. That cancels. What the hell happens here?
Oh, what's this? Why are you confusing me, bro?
Can I just kill those ends?
No, but part of the term.
Nope.
all one.
Oh, that's kind of like P is approximated by this. A confidence interval approximates a mean or a percentage in this case.
So I can put this.
What? I'm sorry, somebody.
X bar.
Why?
Square root of it.
Yeah. You can't divide things unless they have the same root. This don't have no root.
Wow, you ran it on my sheet.
Stop. So how do I rewrite n so that it does have a square root? What is n equal to the square root of? N equals the square root of? Yes, n equals the square root of n squared. Now this kind of shit, what I'm about to do right now, is where you guys go, oh, you math people just do all this weird shit. But do you understand what I just said? I want to do something. Something wants to happen to that stupid thing. So if I just rewrite the bottom with the square root on it, then I'm allowed to reduce. So I'm going to write the bottom as square root of n squared. Now I'm allowed to reduce. What happens between these two?
Cancel the one out on the top.
Yeah, one cancels.
And you get one left.
So now I have this. P is approximated by this. And this is the formula that's on the front of the sheet. Become a big ass square root, Jeff. It's written better on the front.
Hey, that's pretty good.
Hey, it matches.
Oh, thank God. It always sucks when I do a derivation. It's not the same. So this formula is truly the same formula. It's just broken down and rewritten to talk about percentages, not means. So now you just throw everything we know in. Try to finish this problem out. Throw in what you know. We know everything in there, right? We know the z is 1.7, p hat and q hat figured out, n we know. Man, we know it all. So do it. Know it alls.
Definitely not me.
Yeah, you know on a test or a quiz we're going to make the formula sheet, or just like always. You'll have these on a formula sheet. I want to make sure you know how to use a formula.
No, you have to memorize all of them.
The finals is going to be formula sheet. That'd be so evil. You don't need to know it. No, you do. Oh, that would be evil.
Just making sure. I'm like,
Yeah.
Bro, look at all these.
math and study now.
Or be like me.
Shut up, Brandon.
I mean, technically, sort of. I mean, and that's why it kind of
Like
goes
you.
with the p hat.
We're all trying.
Why are people more like me? Yeah, our average is pretty good.
Get rid of what?
Yeah, what do you have?
I didn't
These are 93, right?
the same way we don't get rid of this.
You know,
What does this do?
So what does this do? It approximates percentages. But do you see why I needed this here so I can fill the end? I did really good. And what I know is like I said, this is just derivation of where this
You got 100%.
This formula.
Yeah, you got 100% on the next one. Right, well.
That's the same as this. Yeah.
And then on this one, I got one. It's okay, he's still got this one by one. We just gotta be better. $20 we have a quiz tomorrow.
That's right. We're still
Yes, next Wednesday.
Where's 40?
It's just the chapter.
Wednesday, it's next Thursday.
The 26.
Uh-oh.
What do you learn chapter 11? Because what? I think every check, we only 10 assistants, and this is only 20. Yep.
So for the error here, I get 0.033.
I didn't.
Is that what you guys got?
No.
The error? Just the error piece?
No.
All right. So Z is 1.7, right?
Yeah.
Okay, so 1.7.
Yeah.
That's the square root of
Uh-huh.
P hat, Q hat, divided by N, right? So there it is. 1.7 times the square root of that times that divided by that.
Yeah, I got that.
Your PEMDAS.
What's the matter?
I got 0.0196.
I got the same thing as you.
I do it this way. Fraction.
No.
Oh, you just didn't multiply by 1.7.
Yeah, we did.
Well, he didn't.
Oh.
You didn't.
He didn't.
So I was right.
What's up?
Maybe I did.
Everybody getting that
I
number?
got the same thing you did.
Good, because that's the right thing.
Yeah.
Not just because I'm the teacher man, but because I've looked at it several times now and I know it's right. So again, if you have the old school, if you have the older operating system, it doesn't have the square root become big.
I usually
Anybody have that one kind?
Me.
All right, let me show you what that looks like.
usually
Probably
more because you always want to see it.
From that way.
1.7
Shit. It's just my computer that's that way. No.
times square
Who has that old school?
point. I think I do.
Yeah. All right. So when you do the square root,
You're gonna round the 2 to 3 from the 7.
this is not backlit, so
Oh, shit.
old school. When you do the square root, it opens up parentheses.
The
You do
hell?
not want to close that parenthesis until you get everything in there.
Oh. 1.7.
Bam, now I'm out of the square root. If you close the parenthesis, you're out of the square root. Good old order operations. Please excuse my dumbass son. Better. What have I not done yet? Times 1.7. And now everybody's got the same. I like it. So be careful with order operations. There's a reason we learned that. So let's see. So we got 0.485, give or take, 0.033. So it's like plus or minus 3.3%. Almost the 4% that you see all the time. You see 4% all the time because they actually mostly use 95% confidence interval. So if I use the higher confidence interval, my z-score would have been 1.96. This would have come out to be probably closer to 4%. That's why we almost always see plus or minus 4%. Let's see, what do we get? We get
0.5.
0.52,
1.7, yeah.
0.518.
Yeah.
So we are,
Wait, I got point
Duh.
451.
7. You get to round it.
alright, continuing on. We are 91% confident that,
The interval.
good, and it's not just semantics. You never say we're 91% confident that the real percentage is in, that's the wrong way. The real percentage doesn't fall somewhere, the real percentage is sitting there. We got to talk about it from the aspect of, did my interval catch it? So we are 91% confident that the interval we made, what's that interval?
45.
Good.
0.45.
0.2%.
45.2%, always change it to percentages because that's your units. 45.2% to
51.8%.
51.8%
Contains the true mean of people
contains
that
the
voted.
true what?
Mean.
No,
Mean amount of people
No.
voted in the primary.
we're not talking about
Proportion.
means.
Proportion.
Proportion or percentage.
I put mean proportion.
Don't put mean proportion, because that doesn't make any sense. The true proportion of people that what?
Voted.
That voted.
Whoa, that voted in
In
the primary.
primary. Gucci.
I like it. Yes, sir.
So I have like a different rounding than 0.452.
Okay.
So I didn't do it with the point 0.303 or I didn't do it with the errors. Like I just put this in instead of the decimal that you guys got right here.
That's fine. That's fine. Yeah. All right. Now, just to save you from a little algebra, if you do this, yes. Look at it again. Look at it again. Does it say 485? Okay. The same way we developed this formula, you could could do the exact same thing to develop it from this equation. You see, you can solve for n. So I won't force you through all that. You get this. Same idea. So when am I going to use this formula? When the question is how big of a sample or how many of these, why is that going to be when I use a formula? Because that's a formula for n. And what does n mean? The amount. How big your sample is, right? Okay. So here, how large a sample would you need to take to estimate the true percentage to within 2%? We got within 3.3% with 652 people. Now I'm curious how large would I have to get a sample to be within 2%? So what the hell is this? Okay, 0.02, and that's what? E. I like it. So now we know Z is 1.7 squared times P hat times Q hat divided by the error squared. And again, that formula just comes from the same kind of thing we did earlier, solving for n. Good old algebra saving our ass, as it does. And all it gets is shit on, poor little algebra.
So always use.
Huh? Yes, I will give you E. I won't tell you it's E.
So if it's within
Say again? Within is definitely a possible keyword that could be used. You could say that in different ways. And that's the English language. So then what do you get here? Oh, I'm sorry. Did I steal your calculator? No, this is something else. Mine. I gave you yours back. You gotta watch me when I take your stuff. So you're 1.7 square. Oh, there.
Never mind, I figured it out. Sorry.
I get this.
I don't say.
So 1805. So how large is sample? So 1805. Okay. Do you guys want to take another quick little break, or you want to? Sure. Let's do a quick break. We'll do 10 minutes. Come back at 40 past. I have 2 more things I want to do today. Damn, Jeff.